Hello everyone. Today we will be looking at the experimental part of cyclic voltammetry. If you are watching our channel for the first time, a basic introduction to cyclic voltammetry has already been covered in the previous video. Please watch that video. Coming to the CV instrumentation, a CV system includes an electrolysis cell, a potentiostat, and a current to voltage converter and a data acquisition system. Before going to the video, let me welcome all of you to our channel Cyclic Official YouTube channel. If you like the video, please like and subscribe our channel. In the CV instrumentation, first we can take a look at the electrolysis cell. The electrolysis cell or electrolytic cell or electrochemical cell consisting of two parts. First one is electrolytic solution and the second part is the three electrode system. That is, one is working electrode and the second one is counter electrode and the third one is the reference electrode. The vessel used for a CV experiment is called electrochemical cell or electrolysis cell. The schematic representation of an electrolytic cell is shown here. All of the electrodes, working electrode, reference electrode and counter electrode and the solution and other connections are inserted into a glass solution reservoir. This solution reservoir is capped using a Teflon cap and this blue colored solution is the electrolytic solution. Coming to the electrolytic or electrochemical solution, the solution consisting of three parts. First one is the compound of interest or the function or the solution of metals which needs to study. Generally, the concentration of solution varies from 10 raised to minus 3 to 10 raised to minus 5 molar. And the second part is an electrolyte having a concentration around 0.1 molar. And the third one is the solvent. The solvent selection will be crucial. One must choose a solvent which dissolves both A and B. That is the compound of interest and the electrolyte. Thus together these three parts called the electrochemical solution. The second part in the electrochemical solution is the electrolyte or otherwise called supporting electrolyte. This supporting electrolyte is otherwise known as inert electrolyte or inactive electrolyte. Supporting electrolyte is the electrolyte containing the chemical species that are not electroactive, especially within the range of potential used for the experiment. It has an ionic strength and conductivity much larger due to the electroactive species added to the electrolyte. This electrolyte is widely used when control of electrode potential is required. Let's go much more details on the supporting electrolyte. It is always states that supporting electrolyte do not participate in the electrochemical reactions themselves. Do they really not? Think about it. Before going into this, why we need to use the supporting electrolyte? What are the functions? First one, it reduces the ohmic drop RS. Reducing the ohmic drop is crucial because the resistance of the solution can significantly impact the accuracy of measurement. The resistance of the solution can affect the accuracy of the measurements. And the second one, it modifies the electrode-electrolyte interface by reducing the size of the double layer and favoring heterogeneous electron transfer, which can improve the efficiency of the reaction. Third one, supporting electrolyte will help to increase the conductivity of the solution. And the fourth one is, it is eliminate the transport of electroactive species by ion migration in the EF, simplifying the analysis by maintaining a control through diffusion or diffusion combined with migration. The fifth point is, it will maintain a constant ionic strength. And the sixth one is, it will also maintain the constant pH, etc. As I told earlier, the supporting electrolyte do not participate in the electrochemical reaction. That is, ideally, this supporting electrolyte should be inert and highly conductive. Again, I am telling, it is in the ideal condition. Do we really need the supporting electrolyte? Think about this twice before going to do experiment with the supporting electrolyte. One thing is that the elevated concentration can exert a significant impact on other components within the system, especially in the biological system. Second reason is, even though it helps to make the double layer more uniform, an excess amount can destabilize the double layer. Third point is, we need to add excess amount of supporting electrolyte to the solution, which may result contamination from impurities. That is, there is a chance for contamination from impurities. So depends on your system. Please choose the supporting electrolyte wisely, whether need to use or not. The supporting electrolytes can be broadly classified into four. That is, inorganic salt, inorganic acids, buffer system or the organic solvents. Organic salt such as KNO3, Na2, SO4 and others are commonly used in aqueous solution with the advantage of the redox potential of the positive and negative ions is on the outside of the potential window of water. Next one is the buffer. Buffering system includes acetate, phosphate or citrate and others and are commonly used when controlling the pH of a solution. When an organic solvent is used as a supporting electrolyte, high purity is required. Therefore, it must be thoroughly dried and free of moisture. Supporting electrolyte is commonly used. Halide ions and alkali metal cations are commonly using. That is, the anion part of the commonly used supporting electrolyte is X-, halide ions. Example ClO4-, BF4-, PF46-, OTS-, etc. And the cation is M+, that is alkali metal cation. Example is R4N+. These supporting electrolytes varies from solution to solution. For example, in different solvent, different supporting electrolytes. The table gives an examples for this. Some of them are commonly used in any solvent. For example, in the tetrahydrofuran solvent, LiClO4, NaClO4, etc. can be used as supporting electrolytes. In the acetonitrile case, we can use these supporting electrolytes, and in the dimethyl amide, we can use all of them as supporting electrolyte. And you can see in all these three solvents, NaClO4 we can use commonly. Coming to the third part of electrolytic solution, that is a solvent. How to choose a solvent? The solvent should be liquid at the experimental temperature and can be purified after experiment. It should dissolve the analyte and high concentration of the supporting electrolyte completely. Third condition is it is stable towards oxidation and reduction in the potential range of the experiment. Also, it does not lead to the harmful reactions within the analyte or in the supporting electrolyte. Taking all these points in mind, now you may be in confusion. Which solvent should I choose for my experiment? Solvent A or B? Which one will be better for my experiment? Your choice of solvent and electrolyte should be based on the solubility of your studied chemical and the desired potential range. Some of the examples are shown here. Electrode, platinum or mercury carbon, etc. This I will about this later. If you choose water as solvent, we can take sulfuric acid or buffer or NaOH as electrolyte, etc. If it is MECN solvent, you can use this TBaNF4 electrolyte. These ranges are highly depends on the purity and dryness of the solvent and the electrolyte. In any manual purification step, don't add any undesirable electroactive impurities. This photograph represents an electrolytic solution. This vessel is called electrochemical cell. Now it's simply a solution bottle. Once all the electrodes and other connections are dipped into this solution, it will become an electrochemical cell. The black solution contains compound of interest, supporting electrolytes and the solution. In an electrochemical cell, there is a 3 electrode system other than the electrolytic solution. That is, the first one is working electrode, second one is the counter electrode, and third one is the reference electrode. The electrolytic cell consisting of 3 electrode, working electrode, reference electrode and counter electrode. What is a counter electrode or what happens in a counter electrode? The counter electrode performs an opposite electrochemical process to what is happening at the working electrode. That is, oxidation. If oxidation is happening in the working electrode, means reduction is happening in the counter electrode. Or if reduction is happening in the working electrode, means oxidation in the counter electrode. In this way, counter electrode completes the circuit within the full electrochemical cell. Here is a picture of electrochemical cell with the counter electrode. In most of the case, the counter electrode is platinum wire. Second electrode is reference electrode. The reference electrode provides a well-defined redox couple that electrochemical process occurring at the working electrode and counter electrode can be compared against. Silver reference electrode are typically used in non-aqueous condition with silver nitrate as the silver plus salt. In aqueous condition, a saturated calomel electrode or standard normal hydrogen electrode or silver chloride electrode can be used. And the third electrode is the working electrode. The potential at the working electrode is either scanned or held constant to perform electrochemical transformations in the analyte solution. For analytical scale application, commonly used working electrode is glassy carbon disc, metallic disc of platinum, gold, silver, copper, nickel, etc. Boron doped diamond or edge plane pyrolytic graphite disc, etc. can be used as a working electrode. In this figure, I am showing this electrode of FTO. That is, here the working electrode is FTO glass. In conclusion, the cyclic voltammetry instrumentation system consisting of an electrolysis cell or electrochemical cell, a potentiostat, a current to voltage converter, and a data acquisition system. The potential of the working electrode is varied linearly with time, while the reference electrode maintains a constant potential. The counter electrode conducts electricity from the signal source to the working electrode. A potentiostat is an electronic device that uses a DC power source to produce and maintain a potential while allowing small currents to be drawn into the system without changing the voltage. The resulting current is measured by a current to voltage converter, and the data acquisition system produces a voltogram. If you think the video is useful, please like, share and subscribe our channel. Thank you for watching.